So welcome to session 6 of the Pre-Leaving Cert Algebra revision course. This video is going to take a look at simplifying algebraic fractions, and then we'll have a separate video within the same session that's going to look at solving equations. So generally linear equations, but a couple of quadratic equations as well that have fractions in them initially. We're going to look at 10 key examples for simplifying algebraic fractions. The first 4 are going to be examples of questions where the denominator, the bottom of the fractions, only have numbers in them, and then we'll have a look at 6 examples where the denominators have variables such as x in the fraction. We'll have a look at some trickier examples, questions adapted from the Leaving Cert higher level papers, as well as some trickier Leaving Cert ordinary level and junior cert higher level questions. And then, as usual, if people are looking to practice any particular type of question, we have the bank of past questions and work solutions. So we have Leaving Cert higher and ordinary level questions, and we have some junior cert higher and ordinary level questions. So we jump straight into the first of our examples, where we're asked to write as a single fraction x over 2 plus 5x over 4. Now I'm writing this on the right hand side of the page for now because I want to work through a process where people can see my train of thought as I work down my way through the question. And then on the left hand side, we'll work through the way that I generally do these questions. And so depending on what school you go to or what teachers you've had, you may have different ways of combining fractions or adding fractions together. So this is the process that I use. And like I said, on the left hand side, we'll see the process that we're going to use going forward. But I just wanted to, on the right hand side, kind of develop what we would have learned from adding fractions from primary school a little before we go into the general process that I use. So the first thing I have to say is we have 2 fractions here, and we want to add them together. So if it says simplify, or if it says write as a single fraction, we're looking to take 2 or more fractions and join them together. Before we can add fractions, they need to be over the same number. So we can't add fractions that are over different denominators. Remember, the denominator is the bottom of each fraction. And here we have one fraction over 2 and the other fraction over 4. And so we can't add these unless they're over the same denominator. So what I'm going to do is I'm going to change one or both of these fractions so that they're over the same number. And the way that I decide what that number is going to be is I take a look at the denominators in the question, 2 and 4, and I find the lowest common multiple of 2 and 4. So what's the lowest number that both 2 and 4 both go into? And 2 and 4 both go into the number 4. And so I'm going to make equivalent fractions for the fractions I have so that they are over 4, if not already. And what we can see is that the 5x over 4, well, that's already over 4. And so I'm just going to leave that one as it is. Now, how do I convert x over 2 into an equivalent fraction over 4? So I take the 2 and I divide it into 4. So 2 into 4 goes 2 times. And so I can see I've multiplied the denominator by 2 to turn it into a 4. And if I've multiplied the denominator by 2, to keep it an equivalent fraction, I need to multiply the top of the fraction, the numerator, by 2. So x by 2 is 2x. And so x over 2 is an equivalent fraction to 2x over 4. Now that both these fractions are over the same number, I can add them together. And the way we add fractions is we keep the denominator, which in this case is 4, and we add the numerators. So 2x plus 5x, and we'll just write them together like that. We could write down 7x over 4 at this stage because we know 2x and 5x is 7x, but just to relate it to the way that I'm going to do the question on the left hand side, we'll just write it like that for now. And then finally we add 2x and 5x, so 2x and 5x is 7x, and it's over 4. And so we've written x over 2 plus 5x over 4 as a single fraction, 7x over 4. Now I'm not going to use that method for each question. I'm not going to keep the fractions separate like this, even though you could do that. You could just write each fraction as an equivalent fraction. So I'm going to write it in slightly different way on the left hand side, and that'll be the procedure that we use for most of these questions. So we'll write down the sum again, which is x over 2 plus 5x over 4. And what I like to do is I like to draw a line across the width of the sum that's going to represent our single fraction going forward in the question. The bottom of the single fraction, the denominator, is found by finding the lowest common multiple of 2 and 4, and we already figured out that that was the number 4. And we can refer to this as the lowest common denominator if we like. What I'm going to do for the top of this single fraction, the numerator, is I'm going to divide each of the denominators of the individual fractions into the lowest common denominator 4. And then I'm going to multiply the number I get by the numerators of the 2 fractions. So let's see how that works. we're going to divide 2 into 4, which goes 2 times, and then I'm going to multiply that 2 by the x that's already the numerator of our first fraction. Plus, then I'm going to divide 4 into 4, which goes 1 time, and I'm going to multiply that by the numerator of the second fraction, which is 5x. And so essentially we've done the same process as we did on this version on the right hand side, but I try and just draw the single fraction initially. And this is a little more handy when we go to looking at fractions that have variables in the denominators. Now I'm going to simplify the top. Simplifying the top is just a matter of multiplying it out. So 2 by x is 2x, and 1 by 5x is 5x. And then I keep my lowest common denominator throughout the rest of the sum, which is just 4. And then finally, I simplify the numerator by adding 2x and 5x, which is 7x, and that's going to be over 4. So that's two versions of essentially the same type of method. So the method on the left-hand side just expresses it as a single fraction early on, where the method on the right kind of breaks down a little bit more what we're actually doing in the question, which is expressing each of the individual fractions as an equivalent fraction over the same denominator, and then we're able to add them and get a single fraction in the end. In example 2, rather than adding two fractions, we're going to subtract one fraction from the other. So we have 5x over 3 minus 3x over 4. As before, we're going to draw a line across the width of the sum, and this is going to represent our new single fraction going forwards. I want to change both fractions so that they're over the same denominator, and so I decide what's the lowest number that both 3 and 4 go into, and it's 12. And so my lowest common denominator is 12, and I put that at the bottom of my new single fraction. How many times does 3 go into 12? Well, 3 into 12 goes 4 times, and so I've multiplied 3 by 4 to get 12, so I have to multiply the numerator by 4. So on top I have 4 multiplied by the numerator, 5x, minus, and here I have to decide how many times 4 goes into 12, and 4 goes into 12 3 times, and so I've multiplied 4 by 3 to get 12, and so I have to multiply the numerator, 3x, by 3. So on the top I have 3 by 3x. Equals. On the next line I'm going to simplify the numerator, so I'm going to multiply out the top term. So I have 4 by 5x is 20x, minus 3 by 3x is 9x, and this is still all over 12. And finally I can subtract 9x from 20x, and I get 11x all over 12. And remember, your answer in itself is a fraction. We're looking to write as a single fraction, and so when we get our answer we'll still have a fraction in the question. So to advance it a little further, we have two fractions, but this time there is more terms in the numerators of each fraction. So each of these fractions have two terms in the numerator. So we do the question as before, so we write an equals in the sum and we draw a line across the width of the question. And then we decide what's the lowest number that both 4 and 5 go into. Well, that's the number 20, and that becomes our lowest common denominator. And so we're trying to turn each of these initial fractions into equivalent fractions over 20. And how do I do that? Well, I decide how many times does 4 go into 20? It goes in 5 times. And so I need to multiply the numerator by 5. And then how many times does 5 go into 20? It goes 4 times, and I need to multiply its numerator by 4. Tidying up the top, we're going to multiply out the brackets. So we have 5 by 2x is 10x, 5 times 3 is 15, plus 4 times 3x is 12x, and then plus 4 times 1 is plus 4. And this is all over our lowest common denominator, which is 20. Tidying up the top, I have 10x plus 12x is 22x, 15 plus 4 is 19, and again this is all over 20, and so this is the final answer. And so our final answer also had two terms in the numerator, and this is as simple as we can get this expression. We can't simplify it any further. Example 4 is very similar, just that we have a minus in the middle of this one instead of a plus. So we have 5x plus 1 over 3 minus 3x minus 4 over 5. So we put an equals on the next line, we draw a line across the width of the sum, we decide on the lowest common denominator, which is the lowest number that both 3 and 5 go into, which is 15. And then 3 goes into 15 5 times, and I'm going to multiply that by 5x plus 1, minus 5 into 15 goes 3 times, and I need to multiply that by 3x minus 4. On the next line I'm going to multiply out the brackets, so 5 by 5x is 25x, 5 times 1 is 5, minus 3 times 3x is minus 9x, and we need to be really careful with the next bit. Minus 3 times minus 4 is plus 12. So a minus multiplied by a minus is a plus. And this is all over 15. Equals, on the next line, I'm going to simplify it by joining like terms. 25x minus 9x is 16x. And then 5 plus 12 is 17. And this is all over 15. And again, that's as simple as I can make that fraction. Now, in the 4 examples we've seen so far, our denominators consisted only of numbers. And what we're going to see in the examples going forward is that there could be variables or x's in those denominators. And we want to see what difference would that make to the way that we're going to proceed with the sum. The first thing is that when there's x's in the denominators, it might not be as easy to find the lowest common denominator, or indeed any common denominator. And so what I just want to show you before we go to those examples is that a common denominator can always be found by multiplying the two denominators. Now, it might not always be the lowest common denominator when you do that method, but it will be a common denominator. And that's what we're looking to use when we go forward and use variables in the denominators. So we could have written this question as, on the bottom of the fraction, rather than writing 15, we could have just written down a 3 and a 5 in a bracket. And we know that 3 times 5 is 15, but it's just to highlight that that was the product of the two denominators, the two numbers multiplied by each other. So let's run with that idea as we go into example 5 and we try and find a common denominator where there's x's in the denominators. So in question 5 we're asked to express this fraction 5 over x plus 3 plus 4 over x plus 2 in its simplest form. And when they say in its simplest form, essentially they're asking us to express this as a single fraction. So I'm going to put down my equals, and as I did in the previous examples, I'm going to draw a line across the width of the sum to represent that new single fraction. It's going to be more difficult to find a common denominator given the denominators have x's in them. But we did say in the previous example that we can always find a common denominator by multiplying the two denominators. The product of those two terms is itself the common denominator. So our common denominator is the product of x plus 3 on x plus 2. And because I've multiplied those two terms together to get that common denominator, I know that each of them goes evenly into it. So basically x plus 3 divides into x plus 3 on x plus 2, x plus 2 times, and so I need to multiply 5 by x plus 2 to make it an equivalent fraction. I've multiplied x plus 3 by x plus 2 to get the common denominator, x plus 3 and x plus 2, and so I need to multiply the numerator by x plus 2. Similarly, what do I multiply by x plus 2 to get the common denominator x plus 3 on x plus 2? I multiplied it by x plus 3, and so I need to multiply the numerator 4 by x plus 3. Now, in simplifying this further, I'm going to multiply out the numerator, the top, but I don't actually multiply out the bottom of the fraction, the common denominator. So 5 by x is 5x, 5 by 2 is 10, 4 by x is 4x, and 4 by 3 is 12. And that's all over x plus 3 on x plus 2. Simplifying the top further, I have 5x and 4x is 9x, 10 and 12 is 22, and again that's all over x plus 3 on x plus 2. Now, one way people like to think about this, but this only works if the common denominator is the product of the two terms. So if we have x plus 3 and x plus 2 and we're happy that that's the common denominator, well then we can just multiply the numerator, 5, by the denominator of the other term, x plus 2, plus 4, the numerator, by the denominator of the other term. And so that works when the common denominator on the bottom here, is just the product of the denominators of the other terms. It won't work, we'll see going forward, if we are able to find a lowest common denominator with variables in it. And we'll refer to that when we go on and see some of the examples later on. So let's have a look at another example of one of those. So we have 7 over 2x minus 3. This time we have a minus, and then 3 on 2x plus 1. So as before, we put an equals down, and we draw a line across the width of the sum to represent our new single fraction. The common denominator is the product of the two denominators. So 2x minus 3 on 2x plus 1. Again, that's a term that we know that both 2x minus 3 goes into and 2x plus 1 goes into. 2x minus 3 divided into 2x minus 3 on 2x plus 1 goes 2x plus 1 times, so I need to multiply 7 by 2x plus 1 to make that an equivalent fraction. Minus, similarly, 2x plus 1 I know goes into 2x minus 3 on 2x plus 1, 2x minus 3 times, and so I need to multiply 3 by 2x minus 3 to make that an equivalent fraction. So multiplying out the top, I have 7 on 2x is 14x, 7 times 1 is 7, minus 3 by 2x is minus 6x, and minus 3 times minus 3 is plus 9, and that's all over 2x minus 3 on 2x plus 1. And again, we simplify the top, but we don't multiply out the common denominator. 14x minus 6x is 8x, plus 7 plus 9 is plus 16, and that's all over 2x minus 3 on 2x plus 1. In example 7, we have a number that isn't written as a fraction, and so the first thing to do in this question is just to make sure to write 7 as the fraction 7 over 1. So we're trying to add fractions together, so we'd like all the terms to be fractions before we try and find a lowest common denominator. So I'm going to write down the sum 4 over 3x plus 5 plus 7 over 1. We put down an equals and we draw a line across the width of the sum. Now the question is, what does 3x plus 5 and 1 go into? Like, what is a term that we could write down as the common denominator that both of those go into? And we get it by writing down 3x plus 5. So 3x plus 5, again, is the product of the two denominators of the fractions we have. How many times does 3x plus 5 go into 3x plus 5? Well, we would just have to multiply that by 1. It's already over 3x plus 5, and so we're just going to multiply 4 by 1. Plus, how many times does 1 go into 3x plus 5? Well, we'd have to multiply a 1 by a 3x plus 5 to get 3x plus 5, and so it goes in 3x plus 5 times. That means I have to multiply 7 by 3x plus 5. And again, because the denominator is the product of the denominators, it was enough to multiply the numerator 4 by the denominator of the other term, 1, and the numerator 7 by the denominator of the other term, which is 3x plus 5. Tidying up the top, I have 4 times 1 is 4, plus 7 times 3x is 21x, 7 times 5 is 35, and this is all over 3x plus 5. And finally, we tidy up the numerator by collecting like terms, so we have 21x plus 4, and 35 is 39, and this is all over 3x plus 5. We're going to look at two methods for example 8, because what we'll actually see in this example is that there's a little trick we could have employed at the start of the question to make it easier. But let's do it first of all with the same process as we would have done the previous one. So we have 5 over x minus 3 plus 2 over 3 minus x. So as we would have done in the previous examples, I write down an equals, I draw a line across the width of the sum to represent the single fraction, and then we're going to have a common denominator of x minus 3 on 3 minus x. In other words, the product of the two denominators of our single fractions. How many times does x minus 3 go into x minus 3 on 3 minus x? Well, that goes in 3 minus x times, and so I need to multiply the top 5 by 3 minus x, plus how many times does 3 minus x go into x minus 3 on 3 minus x? Well, that goes in x minus 3 times, and so I need to multiply the top 2 by x minus 3. Or in other words, I'm multiplying the numerators by the denominators of the other terms. Simplifying the top, I have 5 by 3 is 15, minus 5 by x is 5x, plus 2 by x is 2x, and 2 by minus 3 is minus 6, and that's all over x minus 3 on 3 minus x. And then finally on the top I have 15 minus 6, which is 9, and minus 5x plus 2x is minus 3x, all over x minus 3 on 3 minus x. Now, some people will actually spot that this simplifies down further. If you factorize the top, 9 minus 3x, you can take out a common factor of 3, and so the top becomes 3 on 3 minus x, and then the denominator stays the same, which is x minus 3 on 3 minus x. And if I now divide the top and the bottom by 3 minus x, I can see that they cancel, and I have a final answer of 3 over x minus 3. So that's the way we could do the question using the method in the previous examples. So let's have a look at a slightly cleverer method. So I'm just going to write down the sum again, 5 over x minus 3 plus 2 over 3 minus x. And some people might have observed that with the second fraction, we could factor a minus 1 out of the bottom of this and change it into not 3 minus x, but x minus 3. So by factoring out a minus 1 goes into minus x times, and minus 1 goes into 3 minus 3 times. And that allows us to write this now as 5 over x minus 3 minus 2 over x minus 3. So I had a plus and I had a minus, and a plus times a minus is a minus. And now we have the same denominator in both fractions, and so it's just a matter of subtracting the top terms, the numerators, 5 minus 2. And we get 5 minus 2 is 3 over x minus 3. So it may not have looked a lot shorter, it probably took the same amount of lines, but we will see in examples going forward, and some of the trickier examples, that if we can spot a lowest common denominator, it can be a little bit more advantageous than actually just multiplying the two bottom terms together. So in this example, we have 3 over x minus 2 plus 1 over x squared minus 4. And we're going to extend the idea we used in the previous example, this idea that there may actually be a lowest common denominator in this question rather than just the product of the two terms. And so what I'm going to do is I'm going to factorize the bottom of the second fraction. Some people might have observed that x squared minus 4 is the difference of two squares. And so what I'm going to do is I'm going to factorize that separately over here on the side. So I know that x squared minus 4 is equal to x plus 2 on x minus 2. And by doing that, I can see that the product here, x plus 2 and x minus 2, contains the denominator of the other fraction, x minus 2. And so that might enable us to find a lower common denominator than by just multiplying the two denominators we had originally. So let's write it out again. We have 3 over x minus 2, but the second fraction this time is now 1 over x plus 2 on x minus 2. And so when deciding on a common denominator now, I can just use x plus 2 on x minus 2, because I know that x minus 2, the denominator of the first fraction, does go into this. Now, how many times does it go into it? It goes in x plus 2 times. And so to multiply x minus 2 by x plus 2 to get the denominator, I have to multiply the 3 by x plus 2. Plus x plus 2 on x minus 2, the denominator of the second fraction, well, that just goes into our common denominator one time. And so I know that I have to multiply the top by just 1. So it's 1 times 1. Multiplying this out, I get 3 on x plus 2, which is 3x plus 6 plus the 1. And that's all over x plus 2 on x minus 2. And so we'll just tidy that up over here. I have 3x plus 7 on the top, all over x plus 2 on x minus 2. And if we liked, we could have 3x plus 7 over our x squared minus 4. So I know that x plus 2 on x minus 2 is the factorization of x squared minus 4. So if I want, I could just put that x squared minus 4 back in. Now, a useful exercise if people wanted to give it a go is that they could have a common denominator as the product of the original two denominators, x squared minus 4, and then multiplied 3 on x squared minus 4 plus 1 on x minus 2. In other words, the numerators of each fraction by the denominators of the other ones. And if you multiply all this out, it will actually simplify to 3x plus 7 over x squared minus 4. So it's a useful exercise if people wanted to go and give that a go and get to the same answer. But a lot simpler in this example to spot that the lowest common denominator is actually just the denominator of one of the fractions, and it makes it a little bit easier in terms of the multiplication and the simplification at the end. So the final example we're just going to extend to 3 fractions, and we'll see how this becomes a little trickier even though the ideas are the same. So the first thing is to find the common denominator. And again, the common denominator is the product of the denominators of the three fractions. So that's 2 multiplied by x plus 4 multiplied by 2x plus 3. And it doesn't matter the order in which you put these down on the page. We're not going to multiply these out anyway. It's just a common denominator of the product of these three terms. Now, before we actually start dividing the denominators into this common denominator to see what we're going to have to multiply the numerator by, let's just do that work over on the side so people can see more clearly. So our common denominator is 2 on x plus 4 on 2x plus 3. And so if I divided the first denominator, 2x plus 3, into that, what would I be left with? Well, I'd be left with the product of the denominators of the other terms, 2 on x plus 4. So hopefully people can see that. So if I multiplied 2x plus 3 by 2 on x plus 4 to get the common denominator, I'm going to have to multiply 5 by 2 on x plus 4. Minus the middle term, the same thing. We're going to divide the common denominator, 2 on x plus 4 on 2x plus 3, by the denominator of our second fraction, which is x plus 4. And if I divide those in, I get 2 on 2x plus 3. So what do I have to multiply 2, the numerator of my second fraction, by? I have to multiply it by 2 on 2x plus 3. Finally, I have a common denominator of 2 on x plus 4 on 2x plus 3, and I'd like to divide 2 into this, the denominator of the final fraction. So that's going to leave me with x plus 4 on 2x plus 3, and so I'm going to need to multiply the numerator, 3, by x plus 4 on 2x plus 3. Now, we don't have to do this work here on the side. I just wanted to kind of show a little more clearly what we're getting when we divide the denominators by the common denominator. Again, telling us what we need to multiply the numerators by to keep them as equivalent fractions. On the next line then, I'm just going to multiply it all out. One thing we can do if we like before we multiply it out is a lot of people like just tidying up some of the terms. Rather than multiplying the three terms together, we could multiply 5 by 2 to give me 10. I could multiply 2 by 2 to give me 4. And we could multiply a 3 into the first of these brackets to give me 3x plus 12. So that's optional if people want less work in terms of multiplying out on the next line. So multiplying out the top, I have 10 by x is 10x, 10 by 4 is 40, minus 4 by 2x is minus 8x, minus 4 by 3 is minus 12, and then I'm going to open up a bracket here to give me 3x on 2x plus 3 plus 12 on 2x plus 3. Now, I could have done 5 by 2 by x to give me the 10x, and 5 by 2 by 4 to give me 40, minus 4 by 2 by 2x to give me minus 8x, minus 4 by 2 by 3 to give me minus 12, and so on. So it's just a matter of preference as to whether you want to tidy up some of the terms before you do the multiplication or whether you're happy multiplying them as they are. So that's all over 2 on x plus 4 on 2x plus 3. And again, we're not going to multiply that out. We leave that as it is. 10x minus 8x is 2x. 40 minus 12 is plus 28. And then multiplying 3x by 2x, I get 6x squared. 3x by 3, I get 9x. 12 by 2x, I get 24x. And then 12 by 3, I get 36. And that's all over 2 on x plus 4 on 2x plus 3. Finally, I'm going to collect all the like terms together on the top. So I have a 6x squared. I have 2x plus 9x, which is 11x, plus 24x is 35x. I have 28 plus 36, which is 64. And finally, that's all over 2 on x plus 4 on 2x plus 3. And so that's as simple as I can get that fraction. We've taken three fractions and written it in its simplest form as one fraction. So that's the 10 basic examples. If people are looking for more practice at those before they look at some of the trickier examples, you can look at the past bank of Leaving Cert and Junior Cert questions and work solutions in that topic, or you can proceed to the trickier questions where we'll kind of see how this question can be adapted to be asked at Leaving Cert higher level. So let's take a look at how simplifying algebraic expressions have been incorporated into some Leaving Cert higher level questions in the past few years. So the first question here is from the proof by induction topic. So we'll just get it down first of all, proof by induction. So generally a tricky enough topic at Leaving Cert higher level. We'll have done some work in a question and we'll have ended up with this expression k on k plus 1 over 2 plus k plus 1, and we're trying to write this now as a single fraction. So the first thing I want to do is I want to make sure that all the terms in the question are written as fractions, and so I'm going to take the k plus 1 and I'm going to put that over 1 to write it as a fraction. The common denominator in this question is going to be the lowest number that both 2 and 1 go into, which is 2. I'm going to divide the denominator of the first fraction, 2, into 2 to get 1, which tells me I need to multiply my numerator by 1 to make it an equivalent fraction. So I have 1 on k plus 1. Likewise with the second fraction, I'm going to divide the denominator 1 into the common denominator 2, and I get 2, which means I'm going to have to multiply the numerator k plus 1 by 2. I'm going to tidy at the top by multiplying it, so k by k is k squared, k by 1 is k, 2 by k is 2k, and 2 by 2 is 2, and that's all over our common denominator 2. Combining like terms on the top, I have k squared plus k plus 2k is plus 3k, and then I have the 2 at the end, and that's all over 2. And in terms of completing this question for our purposes, that's enough. We've taken an expression and we've written it as a single fraction. In the actual question on the proof by induction topic, we would have to then actually go and factorize the quadratic on top, so we'll go ahead and do that for practice. So we have a k and a k. We're looking for two numbers that multiply to give 2, so that's going to be 2 and 1, and we have to make plus 3k, so it's going to be plus 2k plus 1k, and that's the factorization of our quadratic on the top. And so that little extra step would have to be done in the proof by induction question. Jumping on to example 2, we have a question from the complex numbers topic. So again, just to write down that topic, we would have seen this topic in a few of the examples before, and we would have seen this letter I, and generally when we see I in complex numbers, that stands for an imaginary number. We're just going to treat it like a variable, an unknown in the question, as if it was an x for the purpose of what we're doing, but we'll talk a little bit more about the I towards the end of the question. So writing down the two fractions, we have 1 over 2 plus 3i, and I want to add to that fraction 1 over 3 minus 2i. So I put down an equals and I draw a line across the width of the sum. In this example, the common denominator is the product of the denominators of the two fractions. So 2 plus 3i times 3 minus 2i. I know that if I multiply those two terms together, well then each of those terms will have to divide evenly into that term. So 2 plus 3i, if I divide that into 2 plus 3i on 3 minus 2i, I get 3 minus 2i. And so I'm going to have to multiply the 1, the numerator, by 3 minus 2i to make it an equivalent fraction. Plus, if I divide 3 minus 2i into 2 plus 3i on 3 minus 2i, I get 2 plus 3i, which means I have to multiply the numerator, 1, by 2 plus 3i to make it an equivalent fraction. So now I can add all of the terms on top. I'm going to have to multiply it out first to get rid of the brackets. So 1 by 3 is 3, 1 by 2i is minus 2i, plus 1 by 2 is 2, and 1 by 3i is 3i, and that's all over 2 plus 3i on 3 minus 2i. Simplifying the top further, we're going to combine like terms. 3 plus 2 is 5, and 3i minus 2i is plus 1i, and again that's all over 2 plus 3i on 3 minus 2i. So for our purposes, that's enough work. We've taken the original expression and we've simplified it into a single fraction. In the actual complex numbers question, we would have multiplied out the bottom. So generally we don't multiply out the bottom of our fraction when we're doing this type of question. But in the complex numbers topic, we'll see why it's advantageous now, maybe just to multiply it out. So let's write the question down again. So it's 5 plus I over, I'm going to open up the bracket to have 2 on 3 minus 2i, plus 3i on 3 minus 2i. So the top is going to stay the same. The top is just 5 plus I, and then on the bottom I have 2 by 3 is 6, 2 by minus 2i is minus 4i, 3i by 3 is 9i, and 3i by minus 2i is minus 6i squared. So this is where the question differs from just a normal algebra question. So I isn't really just a normal variable. I is the number square root of minus 1, so it's an imaginary number, and I squared is minus 1. And so what I'm going to do, if I ever see I squareds at leaving cert level, I replace them with minus 1. So let's proceed a bit further. So we go 5 plus I on the top, and then on the bottom of the fraction I have 6. Minus 4i plus 9i is plus 5i, and then I have minus 6 times minus 1. On the top I have 5 plus I, and then on the bottom I now have 6 plus 5i plus 6, and then my final answer is 5 plus I all over 12 plus 5i. Now, believe it or not, there is actually a further step in this question. You would have to do division in complex numbers, which obviously we don't know how to do either. But again, we're concerned with this black writing on the left hand side. Can we take fractions and add them together and make single fractions? Don't over concern yourself with this idea that I squared is equal to minus 1. It's something you're going to see a lot at leaving cert level, but for the people who have seen it before, it was just worth finishing that question, or at least getting down to the part of it where we would have to go then and do some further division. So example 3, funnily enough, also has an I in it, but it isn't the complex numbers topic. This is the topic of financial maths. And so when we're doing financial maths, I stands for interest. And so in this question, I stands for an interest rate that we just don't know yet. So it's a variable, an unknown interest rate to us at the minute. And all we're trying to do is we're trying to simplify this algebraic expression. So we have 1 minus 1 over 1 plus I, and we're trying to make it a single fraction. So I'm going to put down my equals and then my line across the width of the sum. I want to add these two terms together, and so the first thing I'm going to have to do is turn 1 into a fraction, and 1 is just the fraction 1 over 1. So the question is, what's the common denominator going to be? So it's going to be the lowest number that both 1 and 1 plus I can go into, and 1 and 1 plus I both go into 1 plus I. How many times does 1 go into 1 plus I? It goes in 1 plus I times, and so I'm going to have to multiply the numerator 1 by 1 plus I to make that an equivalent fraction, minus, how many times does 1 plus I go into 1 plus I? It goes in 1 time, and so I'm going to multiply the numerator 1 by 1. Tidying up the top by multiplying out the brackets, I have 1 by 1 is 1, 1 by I is I, and then minus 1 by 1 is minus 1, and this is all over 1 plus I. I can see that the top of my fraction, the 1 minus 1 will give me 0 and cancel out. And then I'm left with a final answer of I over 1 plus I. So remember again that this is just a part of this financial maths question. So there would have been more to making the original expression, and there would be more going forward with this question as well. But if we don't know how to simplify algebraic fractions, this little section of the work or step of the work will stop us from actually getting to a final solution. So the final example we've adapted from Leaving Cert papers of recent years is taken from another complex numbers question, but this would have also had a trigonometry aspect to it, so we'll just get that down as well. Trigonometry. And so the variable in this question is n. Now 5 pi over 3 plus 2 pi n. So again, I just want to make the 2 pi n a fraction, and so I'm just going to put it over 1. That gives me a common denominator of 3. 3 into 3 goes 1 times, so it's going to be 1 times 5 pi, plus 1 into 3 goes 3 times, so it's going to be 3 times 2 pi n. And then multiplying out the top, I have 1 by 5 pi is 5 pi, plus 3 by 2 pi n is 6 pi n, and that's all over 3. And so again, this is just a small part of a complex numbers question where it may have been useful just to simplify that fraction before doing the next part in the question. So with those 4 examples, I would say that the difficulty level isn't enormously high, certainly not much more difficult than the 10 basic examples we would have seen earlier. But it's the fact that they're incorporated into the middle of harder Leaving Cert higher level questions. And if you don't know how to simplify an algebraic fraction, you're not going to be able to do that little step, and maybe only 3 or 4 lines of a sum that would allow you to get to the next stage where you'll actually go and solve that question. So well worth having a look at them, even though the topics themselves may be unfamiliar to us. The next few examples are going to be taken from older Leaving Cert higher level questions, and I would say that they have a higher difficulty level. There's little tricks in some of them where the common denominator might not be just as easy as multiplying the bottom of the two fractions together or finding the product of the denominators. So take your time to go at those. When you've had a look at them, have a look at the work solutions that are attached to this session, and if anyone is having any greater difficulty with them and they want a video made on any of those, just let me know and we can do that and post it.